Welcome back to ECE 442. We are 542. We are in the home stretch. As you can see from the dates, they are now getting closer to the final exam. Our final exam is the first day of finals. That's a Friday, and it will be at night from 6 p.m. to 8 p.m. on May 9th. And I just went ahead and established a final exam review session the 15 minutes after our last class, thinking maybe you would be finished with design day, but probably your design day report is due the next day. Who knows? But hopefully you will be able to attend or at least watch. You'll have reading day on Thursday to start getting ready for your finals, which our final is 8 on Friday. I don't know if I can say that enough. There's also teacher course evaluations that you can fill out online. And today what I wanted to try to do was go through three things. One is a review of the PID Controller Example that somebody was asking about via email, and then some other people are saying, oh, I'm using this RL tool, which means root locus tool in MATLAB, and maybe that's one way that you could possibly obtain a little bit more intuitive feel for the root locus if you can set it up properly. And I'm not sure I will be able to do that, but you can correct me when I have mistakes. Then we will get into the general Z-plane controller design, and this will hopefully help you on homework 7 if you haven't already finished homework 7, and in particular the very last problem. You might start with something that's unstable, and now you need to figure out where do I place poles or zeros to possibly allow this root locus, these branches of the root locus, to come back in where I want them, which is inside the unit circle. And probably what will be our last topic of the semester is state space controller design. And we'll break that down probably into 3 or 4 pieces. One will be full state feedback. Then we will try to build up estimators that are full order estimators, and then worry about combining those into a full order compensator. And that full order compensator then we can compare with these other controllers, C of Z's, that we've been designing so far this semester. That's the plan. Here is our PID controller from before. We had an unstable plant, a pole at Z equal 2 in this negative unity output configuration. Our controller is in series or in cascade with the plant. And our PID controller, capital C of Z, has 2 fixed pole locations at the origin and at Z equal 1. And it's our job in the PID controller design to select beta 1, beta 2, and K. We have 3 parameters now to select in a PID controller design. And this is what you will need to be able to do on the final, is how do you figure out where to put beta 1, beta 2, and K to achieve an acceptable result. Last time we said, oh, on our first attempt we said, let's just try locating our triangles, our dominant closed loop poles, with this PID controller at 0.8 plus and minus J 0.2. When we computed the gain K to get us to that point, it actually caused the third pole to go outside the unit circle and shoot off towards Z equal minus infinity. But we were constraining ourselves to having the 2 zeros on top of each other. That's what I'm meaning by beta 1 is equal to beta 2. So we forced that to try to simplify our design process. That was the idea. But that didn't help us in achieving a stable closed loop system with a desired dominant pole location of 0.8 plus and minus J 0.2. So our second attempt said, well, let's change that desired dominant pole location to 0.9 plus and minus j 0.1. That ended up being more difficult to do, and again, it was unstable, keeping the betas equal, keeping the zeros right on top of each other. Then I became frustrated, and I said, I just want to get something that will be stable. Forget pre-specifying a z delta. So that was our third attempt. Let's just forget trying to determine where we want those poles to be. Let's just see if we can get some branches inside the unit circle that will stabilize our closed loop system. And that was our third approach, is forgetting about z delta to begin with. Let's just try to stabilize the closed loop system. So let's do that using MATLAB, and this then maybe will allow you a way to check your answers when you're designing controllers for your homework assignment. Obviously, you won't be able to use this on the final exam, so you're going to have to understand the rules, the techniques that we use, but this might help you develop some intuition into what's going on. And what we will do is we will actually use a sort of built-in tool in MATLAB called RL tool, or root locus tool. So let's see if we can actually do that. And before we do, let me just go ahead and define my plant, which was just a single pole at z equal 2. The numerator was a constant 1. That's the numerator. My denominator then has an expression of 1 times z minus 2. That's the row vector for the denominator coefficients, and then I'm not even specifying what the sample period is, so I'm just going to call that minus 1 and say I have a non-specified sample period for this system. I haven't been told what it is, or I'm not going to use one. That's now my open loop plant, G of Z, let's say. And it looks like what we expected it to be. Now let me initiate the root locus tool feature within MATLAB. So it's setting up a GUI, and hopefully this will sort of work. And there's all sorts of windows that start popping up. Here's our window for the root locus, and I haven't yet given the tool a system to sketch for the root locus, and that's what I want to do first. And so I'll go into this window that opened up automatically, and I will say I'm going to input some system data, and in particular I'm going to, and so before we do, you have to sort of memorize this sketch, this block diagram. Our plant is G. We're using unity output feedback, meaning the H is going to be 1. We're not going to have any feed forward gain or reference input gain. Our F will be 1, and we'll sort of be playing with putting poles and zeros, sprinkling those down in the C, in the controller. So for now, let's just put in some system data, and I'm going to now browse to try to find the G. That's my plant, and I did already define that. I'll say import GD as my G, and actually what I want to do, what I've learned, is that I probably need to put some of my plant or my controller into play also. But before we do, it's now sketching the root locus of that single pole transfer function. Our pole is over there, that x at 2, and our root locus is going to negative infinity on the real line, and that magenta square is the location of the gain that MATLAB has selected. for whatever reason. And so if you put all of this together right now, it's saying, oh, our closed loop pole would be right at z equal 1. And that's right on the stability boundary, and we probably don't want that to be there. Now, if we're designing a PID controller, let's go ahead and build up a controller that just has our poles fixed, and we will actually, with the graphical user interface, we will locate the zeros, the betas, by our mouse. But I'm finding that this seems to work better for what I would expect the system to produce, meaning my closed loop transfer function, my poles are fixed in a PID controller. I'm going to just let my numerator be 1 for now, and I'll put those zeros in the graphical user interface. But my poles are located at the origin and at z equal 1, which means that my coefficients, I need 3 of those. I'll have z squared minus z plus 0. That's my denominator, and since my plant didn't have a specified sampling period, I better not put one for my controller that I'm going to connect it with. And if I didn't know if I had input the data right, I might say, let me check the pole locations of that controller, and in fact they are at the origin and z equal 1. Now let me go back to my window that allows me to input system data, and now we have to remember what was what. C was our controller. Let's import that by browsing to the only variables that are in MATLAB right now, and let's import C1 as our controller. And you can see then that the data for G, the plant, is GD. The data for our controller C is C1. We'll say that's okay. And now let's go back and see if our root locus looks okay. So all we've done so far is we started with a pole at z equal 2. We've now introduced a pole at the origin and another pole at z equal to 1. And that's the root locus that we would have to sketch if somebody said, oh, you have a 3-pole system, right? We haven't yet introduced the 2 zeros that we have the flexibility to select in our PID controller. Does that look consistent with a 3-pole system and no zeros? What's your pole zero excess for a 3-pole system? 3. You have 3 more poles than finite zeros. So you have 3 zeros at infinity, and your root locus branches, all 3 of those branches are going off to infinity, and they're going off in the appropriate directions: 60, 180, and 300. And you can see that those squares, which would indicate the closed loop poles, they're not inside the unit circle, and so we need to do something. Well, the 1 is, but you have 2 that are not. Because of the poles at 1 and 2, those 2 branches coming together and going off to 60 plus and minus 60, they're not going to go into the unit circle. So now let's go up and fetch some of these poles and zeros, and the zeros, luckily MATLAB uses open circles like we've agreed to do. And now you can simply go down here and put 1 in. So now I put 1 in, and that really didn't help too much. It did bring that pole at the origin towards it, but we're still going off. Now what's our pole zero excess? How many branches of the root locus do we have? We had 1 pole from our plant and 2 poles from the PID controller. We have 3 poles in our CG combination. We have 3 open loop poles, so we should have 3 branches. But we just introduced a finite zero. somewhere between 0 and 1. And we can go hover on that if we wanted to with this hand, hopefully. And that hand, if I left mouse it, it'll say, oh, your current location is 0.38. And then I can drag that around if I want, just by holding the left mouse button down and moving that 0. Well, that's only 1 0. We need to put another one in. Question? Well, the question was, can you just introduce zeros all by themselves? And the answer is no. This is now a 0 in combination with those 2 poles in the PI controller. So we're now populating the numerator of the PID controller that we sort of halfway introduced into the system. We put the 2 poles in, and now we're responsible for putting in the 2 zeros, but we wanted to do that graphically. And so now if we put in another 0, now we're looking like it might start to produce something that will work. Is this a stable closed-loop system, as shown? And how do you tell that? You're looking for your 3 magenta squares, aren't you? Those are showing you the locations of your closed-loop poles. And you've got one way outside the unit circle beyond -2, almost a -2.5. So this is now unstable, but you might be able to stabilize that if you lowered the gain. And you can see, if you have good eyes, the current location where that hand is 0.62 plus and minus J.41. And the natural frequency and the damping are indicated. The damping is the ideal damping, and it's going to be messed up by those zeros, which we know is going to be true. I still haven't backed off the gain enough to get that 3rd pole inside. Now I have. Yes? That's a good question. I don't even know. The question was, by default, does MATLAB show the poles when you first do it with a gain of k equal 1? And I think that may be the case. But I would always sort of start to question what it's giving you for the gain, is what I've noticed. And you might want to sort of do this on your own after you've sort of seen what looks like might be working for you. Question? Yes, so if you force a gain in there, it should go to where you have that gain, I hope. But again, I wouldn't believe quite what it tells you, but this starts to give you the shape of what you're seeing. Now, what you can do is you can also look at, so I'm clicking on the analysis and saying response to a step command, and now it's providing me the step response behavior. And there's 2 plots on there, and this is sometimes helpful. Maybe it's not initially. The blue line is actually the response between the reference input R and the output Y. The green is the command input into the plant. That's the signal U going into the plant G. If you don't like all of those things showing up, you can go back here and you can go, let me analyze the plots, and let me get rid of that closed loop between R and U. And now I just see the one plot from the reference signal R to the output Y for the appropriate choice of the poles that I'm showing in this root locus plot. And now what's sort of fun is you can start to in real time, adjust these, and have those step response respond. But by pulling that 0 over, my gain has been adjusted to where now it's driven that pole outside the unit circle. That's maybe not a good thing. If I put it here, maybe that's not so good, but at least I'm stable. And last time what I did, I think, was I started with a 0 at about 0.1, and I'm now going to look at where I'm at. I'm at now about 0.1. Whoops. Have to be good with the mouse. And let me move this one over to about 0.9, just to give me something that I had done last time. And again, this guy went way too far out. So now you can follow that root locus diagram, the 3 closed loop poles, by looking at one and moving it around and increasing or decreasing the gain. And that maybe will help you gain some intuition into this process. That's the idea behind me showing you this today. So now what we're doing is we didn't introduce any kind of sampling frequency. So this time is maybe misleading. This time is really just the number of samples, meaning we are going in maybe a 2 sample period delay, and then we kick up to 2, etc. So we don't know what our sample period is. It was unspecified, but that's just the number. So by the time we get out to about 14 sample periods, we've settled to our final value. What's the deal with the notch at 3 is it's just probably getting kicked a little bit by the changing input because of this pole over here on the negative real axis. So it's not giving you the normal, what I think you were anticipating, this more normal second order behavior. Now you sort of get kicked partway through that first bump, and you start to increase at 3. And you can look at different points. You could left mouse click or right mouse click on that. Oh, my mouse isn't. Left mouse click, and now I've set it on the amplitude, and I can see that the amplitude is 2. And I can go over here and I can say, well, I don't like that. Maybe I want to reduce it a little bit. Or now you've really increased it beyond 2, so now you might say, let me make that be my biggest value of my output. And you now crank the gain up a little bit, and this gives you a little bit of a feel as to what's going on between your poles, zeros, and gain value in the root locus. This was just to give you an idea what's going on. And if we go back to this and we show what the input looks like, let's just remind ourselves of what happens when this closed loop pole gets close to z equal minus 1. Remember what happens to our input, which is the green? It just starts banging back and forth, because of that. Now we have a controller pole that's close to z equal minus 1, and that's not a good thing. So we probably don't want to have closed loop poles that far or that close to z equal minus 1 when we're designing a system. Questions on this? Somebody, I think, asked, where did the z equal to, or z delta of 0.8 plus and minus j.2 go? Well, I threw that away and said, I'm not going to worry about trying to hit a z delta. Let me just see if I can get a stable response. And I somewhat arbitrarily picked a beta 1 to give me a 0 at 0.1, and a beta 2 to give me a 0 at 0.9, because I knew that that would give me a root locus shape that's indicated here, and that would allow me to hopefully provide some dominant complex poles and a third pole not too far into the negative part or close to z equal minus 1. That was the idea. Questions on that? That's a review of the PID controller. Now I need to try to find my way back, wherever that back is. Let's now move to the next topic for the day. And if you're really paying attention, you can see that I have several topics already queued up. Let's now talk about the general Z-plane controller design. In this case, we are sprinkling both zeros and poles. With the PID controller, our poles were fixed at z equal 1 and at the origin. Now we're saying let's be a little bit more generic or more general and allow all of the poles and zeros to be adjustable. And what we want to do is select those alphas and betas judiciously. And what's going to help guide us in that process is our understanding of the root locus. What happens when we sprinkle poles and zeros onto the complex Z-plane? And it's easier, or maybe, yes, I'll just go ahead and say easier to think about this with an example. Let's just assume that we now have a plant, G of Z, that has a 0 at z equal 1. It has a pole at 1/2, and it has another pole at 2. And let's see if we can actually stabilize that. Here's our system. We can sketch what we know. We have a 0 there, and we have a pole here and a pole there. If I connected this with just a constant gain controller, will I end up with a closed loop system that's stable? If this was my plant and I controlled this with a gain, let's say capital C of Z is now a constant, will this produce a stable closed loop system? And how do you determine that? What's the strategy for determining that? Just sketch the root locus for these poles and zeros, correct? And you're using unity negative output feedback, which says that we're looking for the real line segments that belong to the root locus have to have an angle of minus 180. If that's the case, then if we just tried to control this system with a gain, we would have a branch there. How many branches are we going to have? We have 2 poles, we're going to have 2 branches, and this branch. So as we crank up the gain K, that pole, the open loop pole at 2, is going to be going towards the finite 0 at z equal 1, but it's never going to get inside the unit circle. So I've designed this system to be unstable with just a gain controller. Is that clear? And now you have to figure out, okay, where do I sprinkle poles and zeros in the complex Z-plane with my controller to try to stabilize this? Your boss might say, I've got an unstable system and I need you to control it. I don't really care how it wobbles around, but I want it to If I kick it, I don't want it to go flying off. I want it to eventually quit shaking and stabilize. Is it possible to stabilize this with a controller? And what we want to do is actually use our knowledge of the root locus behavior to help us design that controller. I'm suggesting that you already know quite a bit that you can really sort of write down as observations. Observation 1, that's an O. O1, not a 0, but you could do it either one. But the O for observation. Observation 1, we know that with our controller capital C of Z, we can't cancel unstable poles and zeros, or poles and zeros outside the unit circle. We can put poles and zeros outside the unit circle. They just can't cancel poles and zeros. So that's our first observation. We can't cancel unstable poles and zeros. Observation 2, we need this system to be realizable, which really means we want our controller to be causal. It can't anticipate what to do without knowing the past. So now we must keep the controller causal. And what does that mean with respect to the poles and zeros of capital C of Z, our controller? What does that statement mean in capital C of Z? We can't have any more zeros than we have poles, right? We can only have as many zeros as we have poles, and we could have fewer zeros than we have poles. That will provide us or allow us to keep our controller causal. C of Z, whatever it is, when we're sprinkling poles and zeros, we can sprinkle more poles than we can sprinkle zeros. We can sprinkle as many zeros as poles, but we can't put down more zeros. So if the zeros were like salt and the poles are like pepper, we can't make it too salty, right? We have our two shakers, a pole shaker and a zero shaker, and they have to be at least the same level. Or the pepper, the poles, we can have more. Is that clear? All right. We only have 8 of these observations. No, one more. Observation 3. And then you can make up your own observations as long as they're valid. If we look back at this specific problem, and we are trying to control it, we have a branch between 1 and 2 that right now seems to be a little bit stuck. We somehow need to get rid of that branch. Right now, no matter what we do, we have a pole, a closed loop pole between 2 and 1, no matter what we do to the gain. So somehow we have to eliminate that branch between 2 and 1. That's our third observation. Observation 3 says need to eliminate or remove the root locus branch between z equal 2 and z equal 1. Those are our observations. Now let's try some strategies. S1. We had O1, O2, O3. Now we have S1. Let's attack this third observation first. How can we get rid of that branch between 1 and 2? Again, we have poles and zeros we can throw down on that diagram, and we cannot put a 0 on the x at 2, and we can't put an x on the O at 1. Is that clear? We can't cancel unstable poles and zeros. But we can put poles and zeros outside the unit circle. Is that clear? When I say you can't cancel unstable poles and zeros, that does not mean you can't put poles and zeros outside the unit circle. You just can't put them on top of poles or zeros. You can put a pole on top of a pole because you're not canceling the pole. What? If I put a pole on top of that pole, what would happen to that branch between 1 and 2? Now the phase angle condition says, oh, I can't be living between 1 and 2. If I put a pole anywhere to the right of z equal 1, that's going to now cause this little piece between z equal 1 up to wherever to disappear. Meaning, let me now, here's strategy 1. Strategy 1 is I want to now introduce and now you almost have to forget what your mom and dad maybe taught you growing up, which was 2 wrongs don't make a right. Right? Correct? Well, here you can have an unstable plant and you can introduce an unstable controller, and combined they might actually end up stabilizing things. So 2 unstables might be okay. Introduce an unstable pole to the right of z equal 1. So the question was, what happens if you introduce noise between, or a disturbance or something between the controller and the plant? As long as you keep the loop closed, you should be okay. We'll have a stable closed loop system. If somebody unconnects something, you've got problems. Okay, so we're counting on the loop staying closed. If somebody pulls the plug somewhere, now you've disconnected and you do have an unstable open loop behavior between points in your system. So, for this class, in the final, you want to maybe do this fairly quickly. So for ease of design, we already have a pole at 2. Why don't we just put another one right there, and then if we calculate something for that pole, we can basically sort of duplicate it for this unstable controller pole. For ease of design, let's locate the controller pole at z equal 2, which means we have a z minus 2 pole factor in our controller, C of z. What does that produce? if we now look at what we have, and sometimes it's helpful to sort of just draw these again or in sequence. We had a pole, whoops, have to remember what you're drawing though. That's our plant. Now we said, let's go ahead and create a pole in our controller at z=2. Did this help? What's our root locus now look like? Can you quickly sketch those without having to do much accurate sketching? Now what do you have? What's your pole zero excess? Now it's 2, isn't it? So how many infinite zeros do we have? 2. And when we have 2 infinite zeros, where do those angles live? 180 divided by that 2, isn't it? That's your fundamental angle at 90 degrees. And that then tells you how you're splitting the rest. So the other ones at -90 are at 270. And that might, you don't really need to worry about the centroid of that asymptote. You can just say, oh, what's living? Is there a root locus branch between z=1 and z=2? No, because now there's an even number of poles and zeros to the right of any point there. But we do have this guy zipping there, don't we? But these two are going that way, let's say. It's not critical to know exactly, but we've at least eliminated that root locus branch between 1 and 2. Is that clear? So maybe we're helping, but we're still unstable. But we want to bend those branches, those complex branches, we want to bend those over into the unit circle. And how do we draw branches towards something? So now this strategy that somebody is proposing is to, I'll say that's strategy 2. Introduce a 0 to pull the root locus into the unit circle. Let me sketch it again. And you know what I'm going to do? I'm going to make my job a little easier. I'm going to just say, let me just put that 0 right on top of the pole. Can I do that? I can cancel stable poles and zeros. Typically, you don't want to cancel things that are close to the unit circle because those are right near the stability boundary. So probably don't cancel things too close to the unit circle. But this one is at 1/2, so I'm going to go ahead and cancel that. Now what's my pole 0 excess? So what I've done is actually the following. Maybe I should put that in quotes. An easy 0 location would be at z=1/2. So that now my C of z looks like k z-1/2 over z-2. That's now my controller. And what's my root locus look like now? What's my pole 0 excess? 1, isn't it? I can basically forget the X and the O that are canceled, so I could virtually erase that. And now I have a 0 with 2 poles to the right. Ding, 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 ding. Does that ring any bells? You've learned how to draw those root locus diagrams. Now that 0 is the center of a circle of radius, and in this case, since the poles, I located those nice, I don't have to worry about a breakaway. The breakaway is right where those poles are. My radius is a distance of 1. So that now my root locus, to sketch that, I would just have am I done with my root locus? You have to remember that I like to go towards zeros. I've virtually erased that red and blue X, but I still have a 0 here that I'm moving towards, and I have my 0 at infinity. You said my pole 0 excess was 1, so that's now what my root locus diagram looks like. And I have to remember that I still have my unit circle. I need to crank up the gain enough to get me inside the unit circle, but yet not enough to shoot that 1 outside on the real line. Is that clear? The third strategy then, question? This is not a PI controller, is it? This is a general controller. I couldn't use a PI controller for this system. Why? Why could I not use a PI controller for this system? A PI controller would have forced that cancellation of the 0 right on the stability boundary, and I can't cancel unstable poles and zeros. So I would consider unstable something on the unit circle, or even slightly inside. You don't want to be canceling. Even though theoretically it's not unstable, it's not very nice. So a PI controller we can't even use, can we, in this problem? And our controller now, we've pulled out our pole shaker and put one at 2, an unstable controller. We pulled out our 0 shaker and sprinkled one at 1/2. And we just have a first order controller to try to stabilize this unstable system that we started with. Now what we need to do is select the gain K. Select K. To stabilize the closed loop system. Meaning we need to make sure that our gain K, how many branches of the root locus do we have? Now, effectively, theoretically we have 3, don't we? Because we have 3 poles, but 1 is essentially locked down at z = 1/2 because of that 0. We now have a pole that we forced at z = 1/2. But if we sort of forget that, we effectively have 2 branches of our root locus. We need to crank up the gain K to get us at least to those triangles. And then we can't crank it up so much that we move beyond the square. Is that clear? So the gain to get us to the triangle is less because we only have 2, and then they come back together at the origin because of our radius being exactly 1, and then they split off. One goes to the 0 at 1, and the other one zips off to minus infinity. And you can see that those squares are not symmetrically moving, or they're not moving at the same distance, because it takes k from a large value up to infinity to get it to z equal 1, and it takes k up to a large value all the way to minus infinity to get at that infinite distance. So now we have a unit distance versus an infinite distance being traversed for the same range of gain k. What's an easy choice for gain k? If you were on an exam and you had a minute left, you've already sprinkled this down on your paper clearly, legibly, so that I now know, okay, you've got two of the 3 parts completed, 2 points out of 25. Okay, more than that. Now what do you do? So is it easy to calculate the gain k to get you right to the origin? You can find the gain expression, I hope. That's just the magnitude condition. That's c of z, g of z's magnitude equaling 1. In this case, an easy choice, again, easy is maybe relative, but after you've done this a while, you start to see the idea. An easy choice for k is to find k when z is equal to 0. And k, for what we've designed, we had 2 poles at z equal 2, so they have these factors, z minus 2 times z minus 2, so z minus 2 quantity squared in terms of its length. What was our plant? Oh, we can't forget that guy, can we? That 2. So this is coming from the magnitude condition. I now have a 2 downstairs, and I have a 0 at z equal to 1. But I just have to evaluate that when z is equal to 0. It can't get any easier than that, can it, actually? I replace my z's with 0, and I have minus 2 squared divided by 2 times, wow, that's a difficult one, 1. So I could pick a gain of 2 to give me a stable. And what kind of response behavior are you going to produce with this unstable controller? A deadbeat response, because now our closed loop poles are right at the origin. This controller, it's unstable, but we started with an unstable plant. Now we have a deadbeat response for that choice of gain k. And if you were given more time, you could find the range of k for stability. But you know it's centered, or not centered, but it's somewhere bounding 2, isn't it? It can be a little bit less than 2, a gain value a little bit. And if you had your sketch drawn accurately, and you had your dividers or an accurate ruler, you could simply measure the length from there to there, square that distance, divide it by 2, and divide it by that distance. And that would be the gain k to get you to that triangle. And you could do that graphically. The maximum gain is easy to calculate, isn't it? That's the gain to get you to this point, which is z equal minus 1. And you already have found that was supposed to be a square, which is equal to -1. This gain formula now says that I have 3 squared divided by 2, and this is now 2, isn't it? And that should be an absolute value. Is that okay? And this now becomes 9/4, which isn't much bigger than 2, so you need to be, it doesn't take much gain to get you zipping outside the unit circle. This is now K max is 2 1/4. So it doesn't take much to get you from the deadbeat all the way to sort of an unstable system by your choice of gain. Is that clear? And you know how to calculate graphically or numerically. You can now find, because we only have 2 poles, you could actually find that triangle location with a little geometry, knowing that that z delta is at a plus jb, and you know that that's a distance of 1 from the origin. You now know what a squared plus b squared is. And you can find the closed loop characteristic polynomial in terms of k. And you can put all of those pieces together and find the minimum value of gain k. And I think the gain k for a minimum, I know you're going to want to do this and go home and figure that out. So I'll give you the answer in the back of the book. How's that? K-min, you can check me on this. Wow, where is it? Is 1.5. So there's not much adjustment in that gain k in this unstable system for this choice of 0 and pole location. You could change that if I now relocated my pole and 0 in that controller. But I selected the pole and 0 in that controller to make my design easy. I put my pole of the controller right on top of the pole at 2, and I put my 0 right on top of the pole at 1/2. Questions on how you can sprinkle poles and zeros down to create stable closed loop designs? What's observation 1? Never, 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 never do what? Cancel unstable poles and zeros. Is it possible to sprinkle poles and zeros outside the unit circle? Yes. So don't get those two confused. Okay? Because we had to sprinkle a pole outside the unit circle to stabilize the closed loop system. We just didn't cancel an unstable pole or 0. Questions on that? Page 3. I've always wanted to do that. You probably never listened to Paul Harvey, but it was a radio broadcast many, many years ago, and he would read the news. On to page 3. Today, can almost sound like Paul Harvey. He's no longer with us, but he was an excellent newsman. So now I guess if you Google it, you might be able to listen to Paul Harvey. Paul Harvey, good day. That's how he signed off. That brings chills to my head. Wow, doesn't take much, does it? All right, now let's talk about state space control design. Page 3. And to begin with, we are actually going to begin with the most ideal scenario. And the most ideal scenario is to have full state feedback. And you're going, what is that? And How does that compare with what we've been doing? What we've been doing, what have we been grabbing and feeding that signal back? What is it that we've grabbed in our block diagram? The output, isn't it? We've only grabbed one signal, the output, and fed that back and compared it with our reference. What we're suggesting now is you get a system, let's say it has a position, a velocity, a temperature, a pressure. You can measure all four of those and you have the full state, and you can feed back all of those and scale them up and adjust your dynamics of your system. That's what we mean by full state feedback. So here is our assumption to begin with. If we say design a full state feedback control, then we are assuming the following. We're making this assumption. All of our state variables can be measured or sensed. We have access to all of our state variables. We can scale those up by a gain. We could multiply them by 1/2, or we could multiply them by 10. We can adjust that value that we measured. We can scale it, and then we can feed that back in to form part of our input, or to feed back into the system, and feed back all of those scaled adjusted state variables. So now they've been fed back into the system. That's our assumption. When we say full state feedback, that's what we're assuming. Now, to get us back on the same page, let's look at an example of a state space representation. Does everybody remember this? TF to SS. Transfer function to state space. Suppose somebody gives you the following. Suppose they give you a system, G of Z, and they say that that's 3 over Z times Z minus 2. Do you already see a root locus for that system? And a root locus is assuming output feedback, isn't it? And that restricts where the closed loop poles can be. But is this system open loop stable? No. We have a pole sitting out there at Z equal 2. So we have to control this if we want to have something that's not going unbounded with time. So let's create a state space representation of this particular system. G of Z, again, is just this relationship between the input to the system and the output to the system, which is 3 over Z times Z minus 2, or this is now in the denominator, Z squared minus 2Z. And we could, if we wanted to, get that in terms of delays by getting rid of the highest power of Z, which if we now do that, we find that we have Y of Z over U of Z is now 3Z to the minus 2, 1 minus 2, Z to the minus 1. We all together on that. And now the process, or one way, is to go ahead and cross multiply, get just one equation that involves the output and the input. now have that expression, which, again, this is sort of a review for the final. You might need to go state space to transfer function to state space. You now have a lot of these tools at your disposal. In the time domain, we now know that the present output y, and I'm going to put everything else on the right-hand side of that equality, is going to be 2 times the output 1 time step before, and then what? Plus an input term, isn't it? And where is that input in time? Two time steps before our most recent output, isn't it? So that's now our linear, time invariant, time domain representation of that system. Do you see the block diagram for that? You need to by the final. You could think of this in that form, or you could say, you know what? That's equivalent. If I simply adjusted each of these arguments of the time by 2, I could write that as y of n plus 2 equaling 2 y of n plus 1 plus 3 u of n. Is that okay? That's exactly the same dynamic system. It's behaving exactly the same, but now I can start to think about processing that with delay blocks. If I have the output signal y and the input u, meaning let me go ahead and rewrite that to be y of n plus 2 minus 2 y of n plus 1 minus 3 u of n is equal to 0. Now I can build an all delay block diagram that will implement or solve or satisfy this difference equation, time invariant difference equation. Meaning, I can now say, suppose I inject 0 into this summing junction. Or really, it's y n plus 2 minus 2y of n plus 1 minus 3u of n coming into that summing junction. If I now add to that summing junction, I have access to u of n. So let me go ahead. Here's u of n. Let me scale that by 3 and add that in to that summing junction. Now what spits out of the output of that summing junction? It's just that black and red summed up, isn't it? And my y's are now gone. So that alpha 1, that signal, is whatever it was, which is y of n plus 2 minus 2 y of n plus 1. Is that okay? That's what alpha 1 is. I'm now adding 0 to 3u of n, and out pops from the summing junction the result, because I knew 0 was made up of 3 terms. I now added in a term, popping out as alpha 1, and I said I have y's and u's at the present time. Well, I can help myself if I now pass alpha 1 through a delay to generate alpha 2. What's alpha 2? I just delay alpha 1 by 1 time index, right? And if I added something to alpha 2, I have y available. Let me scale y, and y is going to be coming in from here, so let me bring that there. I have y available. Now I'm adding 2y to alpha 2 to produce let's say alpha 3. Alpha 3 now is simply y of n plus 1. I can delay that, and what do I get? Just y of n, which is just that signal, and I said that was y. And now I've built up an all delay block diagram with summing junctions and gains built out of u's and y's, and this is now my all delay block diagram that is a realization of that transfer function or that difference equation. Now, how do I get a state space representation from this diagram? Final exam question. How do I get a state space representation from an all delay block diagram? And I might give you a 50 delay block diagram on the final. Pardon me? Are you making fun of my head? Anything between them. You were talking delay blocks, not my ears, huh? So maybe there's something between my ears, and there's probably going to be something between those delay blocks, but I might not give you a 50 delay block diagram. But it's the same process. When you're dealing with state space, you can play with a big thing. It's not so ornery. It's just now a system matrix and an input matrix. And it could be your system matrix. If I gave you 50 delay blocks, how big would your system matrix be? This would be an easy fill in the blank on the final. It's 50 by 50. It has to be square, doesn't it? All right. So how do we make a state space representation from this? Since there's something between these blocks, these delay blocks. Do you remember the strategy? We simply assign the outputs of the delays as state variables. And this is where you hopefully understand that a state space representation is not unique. I could make this location on the far right, I could call that x sub 1, and you might call it x sub 2. I'm going to call this next one, which is alpha sub 2, x sub 2, and you might have called it x sub 1. It's the same system, you just labeled it differently. So the state space representation is not unique. Let me now call this x1 at time n, and this is now x sub 2 at time n. Where is x sub 1 at time n plus 1? That's what I need, don't I? I need some n plus 1 x's equaling something times an nx plus something times a u at the present time. Is it clear that this signal is x sub 1 of n plus 1? And this signal, the way I have defined my x's, that signal is x sub 2 of n plus 1. So that now I can create my state space representation. I have x sub 1, x sub 2, both at n plus 1. Those will be a square 2 by 2 matrix, x1 of n, x2 of n, plus a 2 by, I only had one input, u of n. And now x1 of n, that output of that summing junction has to equal the inputs of that summing junction, and I have it equal to x2 of n and 2 x1 of n. And was there any input u directly coming into this rightmost summing junction? No. So my top row in the input matrix is 0. x sub 2 of n plus 1. What's in my bottom row of the system matrix? How many x1s and x2s are going to come in to create x sub 2 of n plus 1? Nada, right? And then what's y of n? My output equation, I only am saying I have one output. That was how I defined x1. So this is now 1, 0. And what we're saying with full state feedback is that I have access not just to y, but I can physically now measure x1 and scale that and feed it back, and I can measure x2 and feed that back. Now I have two parameters that are independently scalable, and I can feed back to adjust the dynamic behavior of my system. And we'll pick up at that point on Wednesday.